Hey guys, welcome back to Chemistry TV. Now let's focus our attention on what how to draw enantiomers and diastereomers under what optical isomerism is called stereoisomeric, also chemistry. And we have done the first video. Now we have done our previous video where we talk about how to identify a chiral carbon and numbers of possible stereoisomers. If you have not watched that video, I will advise you to go check out that video, because that video I taught how to identify a chiral carbon and how many possible stereoisomers can a molecule have. Do you understand? But today we are moving it further. We have to learn how to draw enantiomers. So the question now be, what are enantiomers? What are enantiomers? Enantiomer. We talk about the word enantiomers. Enantiomers. What do you mean? Enantiomers, these are chiral molecules and they are non-superimposable mirror what image. I'll go again. These are chiral molecules and they are non-superimposable mirror what image. So let me break it down here. I said these are chiral molecules and they are non-superimposable mirror what image. Are you there? Okay, look at it here. These are chiral molecules and they are non-superimposable what mirror what image. So you know what taking of this key here, chiral molecule are non-superimposable. So what's a chiral molecule? Right there. And what do you understand by what non-superimposable? Please pay close attention here, because I really want you to get the fundamental before you start knowing how to draw enantiomers and diastereomers. Right there. So I said that enantiomers, these are what chiral molecule and they are non-superimposable mirror image. Now, if you check our last video here, I said that a chiral molecule possesses a chiral carbon, and a chiral carbon is that carbon atom that have 4 different groups attached to it. So if you look at this compound here, C, B arrow, hydrogen, fluorine, and what chlorine. The name of this molecule is called bromochloromethane. Are you there? So bromochloromethane is a chiral molecule. Now, why is it a chiral molecule? Because the carbon atom have 4 different groups. It have what hydrogen, it have what fluorine, it have what chlorine, it have what bromine. So it's a chiral molecule. So now all chiral molecules have non-superimposable mirror image. So when we talk about non-superimposable, it means that they cannot overlap. Let me give you an example here. Your left hand and your right hand. Do you understand? Your left hand, let me give you an example here. Your left hand and your right hand, they are called mirror image of what? Of each other. So let me just say this is what is a mirror, right? Now, if you should place your two hand, your left and your right hand there, if you find that they are what mirror image of each other. Do you understand? Now, see, they are mirror image of each other here. They cannot what they cannot meant to what overlap with each other here. So the word non-superimposable means that they cannot overlap, in the sense that there's no way you arrange here that you can overlap with each other one here. So when you talk about non-superimposable mirror image or non-superimposable, it means that the two compounds cannot overlap with what each other. Do you understand? There's no way they can overlap with each other. So chiral molecules and their mirror image are what non-superimposable. It means that they cannot overlap with what each other. Do you understand? So that what we mean by what non-superimposable. So if you should draw this one is a chiral molecule here, right? This one is a chiral molecule. This one is a chiral molecule here, right? Now the reason why it's a chiral molecule because it have carbon that have 4 different groups right there. If you draw the mirror image of this guy here, you see something like hydrogen, carbon, bromine, chlorine, and fluorine. Can you see that here? you find that this guy is a mirror image of this guy here. Right there. These two, A and B, now because they cannot overlap with each other here. Now the relation between them is called what? Enantiomers. It's called what? Enantiomers. Just so a chiral molecule and its what? Non-superimposable mirror image are called what? Enantiomers, because they cannot what? Overlap. Just so in our last class here, I taught you guys how to what? Identify chiral what? Center, and I taught you guys how to what? Get what? Numbers of what? Possible what? Stereo what? Isomers. So we are going to recap on that idea. So numbers of stereoisomers in which a chiral molecule will have depend on the chiral what? Center. I'll go back again. Numbers of possible stereoisomers a chiral molecule will possess depends on the numbers of what? Chiral what? Center. So we have a simple formula to do that here. Numbers of isomers, numbers of stereoisomers is equal to what? 2 raised by what? N. Idea. 2 raised by what? N. Where N means what? Where N means what? Numbers of what? Chiral what? Center. N equals to what? Chiral what? Centers. Idea. So if I have what? If a chiral molecule have a chiral center of 2, N equals to what? 2. That is numbers of stereoisomers. Numbers of stereoisomers is equal to 2 raised by what? 2 will go to be what? 4. Just you go to be what? To be 4 here. So now let me just give you a little recap here. So I've done so here enantiomers. As we move on, you understand this one here. Just I don't know what you process here, but I believe that you now understand what's called enantiomers, right? A chiral molecule and this what? Mirror image are called what? Enantiomers. So all chiral molecules have that mirror image. So the relation between what? The chiral molecule and this mirror image, that is what's called what? Enantiomers. So there must be what? There must be mirror image to what? To each other before they can be what? Enantiomers. Do you understand? So now, another thing I want to show here is this. Please pay close attention here. So remember, I told you that I want to show you how to draw enantiomers, right? So therefore, let's draw the structure of this one here and check what numbers of what possible what stereoisomers. Right there. So you have 2 chloro-1-butene, which is going to be 1, 2, 3, 4. Right there. So butene means what? There's a double bond here. I can't about 1. So I can't I have butene here. I can't about 3. I have what? So I can say 1, 2, 3, 4. I can't about 3. I have what? A chloro here. I have what? A chloro here. Very important. I have what? A chloro here. So now because before you can what? Identify the numbers of chiral center, therefore you must draw the structure, which I have done in the last class. But I'm trying to recap again in case you have not followed up the last class. You can still understand what I'm doing here. So now here we have 3 chloro-1-butene. We are trying to draw the structure. So 1-butene is what? Is the parent name. That is double bond is account number 1, 4 carbon. Chlorine is account number what? 3. Do you understand? So the next thing you want to put here is what? Hydrogen. Hydrogen, 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 and what? Hydrogen. Can you see that? Now, here we have only 1 chiral carbon. Do you understand? Because a chiral carbon is that carbon out that what? 4 different groups. Do you understand? So it is only this guy that have 4 different groups, because here we have here we have chlorine, Cl, you have the other here we have the all of this one here. Do you understand? So if they ask you now, how many possible stereoisomers can we get from here? Do you understand? How many possible stereoisomers? So here you can say numbers of stereoisomers because of 2 raised by what? N, right? So because here we have 1 chiral center, right? It's going to be N equals to what? 1. So numbers of stereoisomers equals to what? 2 raised by what? 1, which is going to be what? 2. That is, this guy have 2 possible what? Stereoisomers. It means that this guy have about 2 possible what? Stereoisomers, as easy as that. It have about 2 possible what? Stereoisomers. You get? So, but how do you draw the what? The stereoisomers? Do you understand? How do you get the positive stereoisomers? How do you draw the structure? We are going to show you. We have to use a Fischer projection to get it. understand? So, which I want to show you here, we have to use our Fischer projection to achieve that. The next is what? 2-phenyl, 2-butanol. No, 3-phenyl, 2-butanol. So, let's draw the structure here. Let's draw the structure of this guy. So, here we have 1, 2, 3, 4. Right there. 1, 2, 3, 4. 1, 2, 3, 4. So, here we have 1, 2, 3, 4. Right? So, I can number 3 I have a phenyl group. Just a phenyl group. So, here we have a phenyl group here. Right there. Then account number 2, I have what? OH. Just so you have hydrogen, 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 what? Hydrogen. Just so how many possible stereoisomers, how many possible chiral centers do you have there? Here we have 2 chiral centers. This guy and this guy here. Just so how many possible stereoisomers? So my n here is 2 because here we have 2 chiral center. Please go and watch that video. If you know that you don't understand what I'm doing here, please go and watch that video on how to identify chiral carbon. Just because I don't want to spend much time on that because we have already done that before. So here we have n equals to 2. So numbers of stereoisomers equals to 2 raised by what? 2, right? You got to give what? 4. If now this guy have what? 4 possible what? Stereoisomers. Do you understand? So now, how do we get the 4 possible stereoisomers? How do we draw them? Do you understand? So this stuff we really want to what? Repair classification in this class, and this is what I'm going to explain to you. Do you understand? Okay, now, so to draw enantiomers, do you understand? To draw what? Enantiomers, we can use a simple formula which is called Fischer Projection Formula. Right there. Now, Fischer Projection Formula is one of the easiest way you can draw a chiral molecule and their possible stereoisomers. And Fischer Projection is very easy. It only uses vertical and horizontal line. Right there is a shortcut to drawing compound in 3-dimensional structure or 3-dimensional shape. Do you understand? Imagine here we have this kind of shape here. Right there. We have this kind of shape here, right? In 3D. You find that if you check on here, there are some that is projecting towards the viewer. Do you understand? If I check on here, if I should point on here, it's pointing towards you. That is, you can see the object, right? So in 3-dimensional shape, there are some object that is projecting out of the plane of the paper. So they are projecting out of the plane of the paper. Why some objects are projecting back to the plane of paper. So it's just like if I should stand here and I point you, just stand. Now this hand is pointing towards here. But if I carry my hand back, like for example, now I carry my hand back like this and I'm facing here, you find that this hand is projecting forward. Why is projecting backward? Do you understand? So in 3 dimension or a 3-dimensional shape, now there are some objects that project out of the plane of the paper. Why there are some objects that project back of the plane of the paper? Do you understand? This is what. So because you don't want to use those bonds here. Now use what? Fischer Projection Formula. And Fischer Projection Formula represents vertical and horizontal bonds. You have to pay close attention here. Now this vertical and horizontal bond represents this type of. It represents different type of bonds. Right there. So you can see that vertical bonds or vertical line represent bonds projecting back of the plane. I don't know, out of the plane of the paper. Right there. So vertical bonds represents bonds projecting back of the plane of the paper. So now when I see a vertical bond like this, it represents out of that project out of, just like you see me here, this hand is projecting forward, white one is projecting backward. Just stand. So now we're talking about vertical bond here. It represents the one that projects backward that you can actually see. Do you understand? Why horizontal horizontal. Why horizontal bond represent bonds projecting out of the plane of the what paper towards the what viewer. Right there. So now here we have the vertical bond and here we have what horizontal bond. The vertical bond represents what the bond pointing away from you, back of the plane of paper. While the horizontal bond represents the bond that projects out towards what the viewer. Do you understand? So we have the one projecting forward and we have the one projecting what backward. Do you understand? So this bond that projects forward represents the horizontal bond. While that projects backward is represent what the vertical bond. Do you understand? So you have to understand this here. So when I talk about Fischer projection, is what vertical and what and horizontal what bond. Do you understand? Horizontal bond means what is projecting towards viewer, while the vertical bond represents what it represents projecting it represents bond projecting back of the plane of the paper. Do you understand? It's very important you understand here because in our next video where I want to show you how to write or draw R and S configuration, this will play a big part of it. Do you understand? So since now understand this here, Fischer projection represents what vertical and horizontal, but it's a shortcut of what draw compound in three-dimensional shape. Do you understand? Taking here that in Fischer projection, the point of intersection between what the horizontal and vertical bond represent what a chiral center. So you can say that the points of intersection between vertical bonds and horizontal bonds. The point of intersection between what vertical bonds and horizontal bond is the chiral center or carbon. Idea very important. It's very important you know this here. Please take it down. So when you're drawing Fischer projection, you use what vertical and horizontal line. Idea vertical represents what the one that projects back. Horizontal means what projecting what forward, right? So the point of intersection between the vertical and horizontal is called what the chiral center. Do you understand? So that point where they meet is called the chiral center. Idea. So it not depends on the numbers of chiral center you have in that molecule. If, for example, here we have this stuff here, let me write this place here. Here we have bromo, chloro, fluoro, methane. Idea is like this: a carbon here, bromine, chlorine, hydrogen, and fluorine. And what? Yes, and fluorine. Idea. So this carbon here carry what 4 different groups. So to draw the Fischer projection here is very easy. So because it only have one chiral center, it only have what one. It have only what one chiral center. It have only what one chiral center because it have only one chiral center. So it's like this here. Now, how will you now place the rest group that is attached to the chiral atom here? You cannot place it in any order you wish to place it. Just it now depends on you where to want to place it. So I can start to place on here hydrogen here, chlorine here, bromine here, and fluorine here. I have successfully drawn a Fischer projection of bromo, chlorofluoro methane. I have successfully drawn this one here. This is a Fischer projection of this guy. It's very easy. Just now to draw the enantiomers is very easy. Imagine you have what? Let me write this out. Imagine you have a mirror. Imagine you have what? A mirror. Imagine you have a mirror. Now draw the mirror image of this guy. If you draw the mirror image of this guy, you have what? CL H F and what? B what? Arrow. Can you see that? So they are what? Enantiomers. They are what? So a chiral molecule and its what? Non-superimposable mirror image are called what? Enantiomers. So these two are not the same because they are different configuration. One is X, one is what? That is going to be our next video. How to assign R and S configuration to what? Chiral what? Molecule. Do you understand? So this one, okay. So one is X, one is what? Arrow configuration. Do you understand? So to draw the enantiomers here is very easy. Is what? It's very, very easy. What we want to do here is that identify the chiral center. If it's one or two, identify them. Do you understand? Then draw your vertical and horizontal. Then put it in any what way you want to put it. Do you understand? Let's take another example here so you understand it. Okay, now let's draw the enantiomers of this guy here. Right there. Let's use the Fischer projection to draw the enantiomers of this one here. So how do we do that here? How do you do that? So therefore you have to what? Draw the structure. Do you understand? So it's going to be 1, 2, 3, 4, right? The doubles are coming by 2. Right there. Chlorines are coming by what? 3. So we have hydrogen here. Hydrogen, 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 and hydrogen here. Just understand? So how many chiral centers do we have? Here we have one chiral center. This is called the chiral center. Right there. So you can do it like this as well. CH2 double bond CH. You can always CH3 and what? Cl. Here we have Cl. Yes, here we have Cl. So this one is 1. This one is what? 2. This one is what? Is 3, and this one is what? Is 4. Can you see that? So now let's draw the enantiomers. Just on, let's draw the enantiomers. Let's represent in what? Fischer projection. Remember, in Fischer projection here, how many chiral centers do we have here? Here we have one chiral center. Right there. So there is going to be one point of intersection. So we're going to be like this. So that is it. So this point of intersection means represent what? The chiral what? Carbon. Just on. So these 4 points here represent the 4 different what group here. So yeah, you can place it any order. Now you are the one that will decide to place it in any order of which you want to place them. Just it does not mean it does not mean that you must place anywhere. As far as you have identified the chiral center and draw like this, then you can place it in any what order. Just so the next thing I want to do here is what? Is to place chlorine here. Now you can also decide to place chlorine here, but I'm place chlorine here. I'm placing hydrogen here. Then you have CH2 double bond CH. Can you see that? 0 is 1. 0 is this guy here, right? Now I place hydrogen here, chlorine here. Then here we have what? CH3. So you can decide to put it in any order. You can also decide to put like this. You can decide to put it like this. Now you can decide to put it like this. Hydrogen, CH3, CH2. Then here we have what? Cl. So it's totally up to you. Just it's totally what? Up to you. Now next what to do here is to what? Draw the mirror image of this guy. So the mirror image of this guy, you just imagine there's a what? Mirror here. Right? So draw the what? Mirror image of this guy here. So you have hydrogen, CH double bond CH2, right? Here we have what? Cl, and here we have what? CH3. Just so they are called what? Enantiomers. Remember, enantiomers. These are what? This is what a chiral molecule, and this is what? Mirror what? Image. So this guy is a mirror image of this guy here. Just so remember, if my n is 1, how many possible stereoisomers can you get? It's 2. Just because it's going to be 2 raised by what? N, which is going to be 2 raised by what? 1, which is what? 2. So now when a chiral molecule is having only one chiral center, the possible stereoisomers is going to be 2. Itself and this what? Mirror what? Image. Do you understand? I want you to understand here. So when a chiral molecule only have one chiral center, it's going to be what? Its structure and its what? Mirror what? Image. Do you understand? So these are what? The two structures. These are what? The two structures. A and B are not the same structure. They are totally different structure. Do you understand? That is why the definition of stereoisomer is that this type of what? Isomers in which compounds have the same molecular formula and structure but differs in their configuration. Do you understand? So stereoisomeric or stereochemistry deals with what? Compounds that have the same molecular formula, the same structure, because if you check very, they have the same structure, but differs in the what? In the configuration. Difference in what? In the configuration. That is difference in what? In the arrangements. Do you understand? So yeah, A and B are not the same. In our next class, we find out why they are not the same, because one is going to be X configuration, one is going to be what? R what? Configuration. Do you understand? So now, when a chiral molecule only have one chiral center, when a chiral molecule only have one chiral center, it's very easy. Just draw what? Just draw the Fischer projection of that compound and draw the what? Mirror image. Finish. You are not doing anything again. Now, it now becomes complex, so you have two or more chiral centers. Do you understand? So when it becomes complex, when you have two or more chiral center, this is where diastereomers now come from. Do you understand? This is where diastereomers what? Diastereomers. These are what? Stereoisomers that are not mirror image of each other. And you can get diastereomers when you have a chiral molecule that have two or more chiral center. So you can only get diastereomers when a chiral molecule have two or more chiral center, which I'm going to explain to you now. But understand that diastereomers and enantiomers are not the same. Enantiomers, they are isomers, they are stereoisomers that are what? Mirror image of each other. Do you understand? So when we talk about enantiomers, they are what? They are stereoisomers that are mirror images of what? Each other. Why diastereomers? They are stereoisomers that are not what? Mirror image of what? Each other. They are not mirror images. You understand? So now let's take one good example here so you understand this thing very well. Now if they should ask you here to draw the what? Stereoisomers of this guy here, how are you going to draw it? If you are being asked to what? Draw the stereoisomers of this guy, how are you going to draw it? Therefore, draw the normal structure here. 1, 2, 3, 4. I there. 1, 2, 3, 4. Can you see that? I can number 2. I can number 2 have what? OH. And I can number 3 have what? A phenyl what? Group. Can you see that? So next is going to be what? Hydrogen. Hydrogen. And what? Hydrogen. Here we have hydrogen. 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 Hydrogen and what? And hydrogen. Do you see that? Here we have what? 2 chiral center. Here and what? And here. Can you see that? So here we have 2 chiral center. So it's going to be CH3 COH hydrogen. Here we have CH and what? And the phenyl group. Here we have what? CH3. This is that. So here we have 2 chiral center here. So when a chiral molecule have 2 chiral center here, have 2 chiral center, the possible numbers of stereoisomers is going to be 4. Do you understand? So when a chiral molecule have 2 chiral center, the possible stereoisomers is going to be what? 4, like what I've done before, right? So the question now be, how do we draw the stereoisomers, and how do we identify enantiomers and what? Diastereomers. Do you understand? So now remember, here we have 2 points of intersection, right? So because we have 2 points of intersection, sorry, here we have 2 chiral center. Remember, you are using what? Fischer projection. Here, Fischer projection, you are using what? Vertical and what? And horizontal line. Do you understand? So the point of intersection means what? Chiral center. Here we have 2 chiral center, 1 and 2. Remember, here we have to start from 1, 2, 3, and 4, right? So we're going to be what? 2 points of intersection here, 1 and what? And 2. This is that. So this is it. So here we have 1 and 2. So they are the what? 2 points of what? Intersection, which are what? The 2 chiral center. So here going to be what? My first one here. We're going to be what? CH3. Here we have what? CH2. Look at something here. Here we have 1, 2, 3, 4. 1, 2, 3, 4. Can you see that? So this one now is now what? CH3, 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 CH3 here. Now here we have the single carbon here. Is having OH and what? Hydrogen. So I can put OH here and hydrogen here. Can you see that? Next one is what? Is this one here? Can put what? Hydrogen here and what? And a phenyl group here. And what? And a phenyl group here. And a phenyl group. This is that. So this is a what? Is what? It is the diagram using what? Fischer projection. So you can look at something here. must you understand the key concept of drawing Fischer projection formula. Using Fischer projection formula to draw enantiomers and diastereomers. Now you can do it in whatever way you want, you wish, but it's still going to be what correct. Just now here I can switch to what put hydrogen here, OH here, put this on here and put this on here. Just so this is what is my number one. So I have drawn what my first stereo isomers. So this is going to be what my first stereo isomers. So now remember, a carbon molecule have two. The carbon molecule have two. A carbon molecule have two carbon center here. Can have four possible stereoisomers, right? Now you have drawn one, left what three. So the question will now be, how do we get the remaining three? That will now be the next question. Now to get the remaining three, now let's get the next one here. Remember, I can draw the mirror image of this guy here, right? If I draw the mirror image of this guy, what am I going to get? I'm going to get this one here. Here we're going to be H, O, H. Here we have what this one here. And here we have what H. Here we have what CH3. And here we have what CH3. I have got what 2. Just that I've got what 2. So here we have A and what B. So these two are what mirror what image. As easy as that. Now, how do we get the next one here? Now, this is where the manipulation comes in here. Now, this is what I'm going to do here. I'll come here and flip this one here. I'll carry this one here, carry this one here. So I'm going to draw on that structure here. So this is what I'm going to do here. Let this one move here, let this one move here. So I'm going to be what? OH and what? And H. Here we have this one CH3 and here we have what? CH3. Do you see that? Now, they also remain the same. Here I have this one here. So don't mind. So let me just call this one out so you understand. And here I have what hydrogen. Now, what have I done here? I have drawn what I have succeeded drawing on that structure here. This structure is different from what this structure. These two are what mirror image of each other. Do you understand? Now I have to draw because I have 4 possible stereoisomers. I've got it 2. How do I get to what the third one? By moving one of this one here. So I can either move one here or move one here or this one here. So the sharing will not be at the chiral center. So you can either move the first or the second one. Do you understand? So I try to move this guy down here and so here. I'm not getting what this first solution. So this guy is not the same thing with this guy here. Do you understand? Because here CH3. Here we have phenyl, hydrogen, and hydrogen. But guess what? This one is at the right, but here is what is to the left. Hydrogen is on the left, but here is on the right. Do you understand? So you have got it on that one here. To get it, so you're going to be what the third what enantiomer, the third what stereoisomers. To get the last one here is very easy. Just draw the mirror image of this guy. So if you draw the mirror image of this guy, right here, so going to be CH3, right? You're going to be what? CH3. Here we have what? Hydrogen, OH, H, and what? And the phenyl group. And the what? And the phenyl group here. Can you see that? So here we have 1, 2, 3, and what? 4. You see that? So now this is where now I want to understand here. I want to be able to identify what's called chiral center. No, enantiomers and what diastereomers. Because the main thing you want to do is what drawing of enantiomers and what diastereomers. Just and so here we have what 4 possible what stereoisomers of this compound. 3-phenyl, 2-butanol. Now remember I told you that enantiomers, they are what mirror image of each other, right? So structure 1 and 2 are enantiomers. Right there. So here we say I and what I are what are enantiomers. Right there. Just because they are what mirror image of each other. So what is the enantiomers again? They are what mirror image of what each other. So these two are what mirror image of each other. Now 3 and 4, they also what enantiomers. So 3 and 4 are what enantiomers. Are what enantiomers. They are what enantiomers. Now, but before that, 1 and 3, they are stereoisomers. of what? They are what? Stereoisomers of what? 3-phenyl to butanol. But they are not what? Enantiomers. Now, why are they not enantiomers? Because this guy is not a mirror image of this guy. This guy is not a mirror image of this guy. This guy is not a mirror image of this guy. And this guy is not a mirror image of this guy. So you can see that structure 1, 3, comma, structure 1, 3, structure 1 and 3, comma, structure 1 and 3, structure 2 and 3. Can you see that? Structure 1 and 3, structure 2 and 3, structure 1 and 4, and structure 2 and what? And 4. They are what? Diastereomers. They are what? Diastereomers. Can see that diastereomers. They are what? Diastereomers. They are what? Diastereomers. Do you understand? So these are to what? These are to draw your enantiomers and what? Diastereomers. Remember, this is what is a series video where I teach you optical what isomerism step by step. Do you understand? So this is going to be what second video in this series. All these videos is helpful because I want to end our class here. Now more video will be coming up to help you understand this thing better. But so far, if this video has been helpful to you, please leave a message that this video is helpful and you got a lot of value from this video. Now leave at the comment section where you understand more. You get. And if you have any question, please kindly leave it at the comment section. I will respond to that. Get. So we are done with this video. Thanks for watching. See you in my next video.